Hello and welcome to the first International Postdoctoral Forum for the Philosophy of Science. My name is Alan Love. I'm director of the Minnesota Center for Philosophy of Science, and I am really excited that we are launching this new initiative. This is something that we hope is a way to lean into the conditions of the COVID pandemic and have intellectual conversations around philosophy of science that can be experienced and joined by scholars from both the University of Minnesota and all over the world. Today, we are happy to have Carina Prunkl, who's coming to us from the Future of Humanity Institute at the University of Oxford. She is currently a research affiliate at the Center for the Governance of AI at Oxford, in addition to her role as a senior research scholar in the Future of Humanity Institute. She also is an affiliate of the Black Hole Initiative at Harvard. Prior to those recent appointments, she was doing her doctorate in philosophy at the University of Oxford, and the thesis title was The Scope of Thermodynamics. She's published a number of papers on that topic, such as on the equivalence of thermodynamic and von Neumann entropy in Philosophy of Science that came out this year, as well as some new work that is in association with the Future of Humanity Institute, such as a recent report toward trustworthy AI development, mechanisms for supporting verifiable claims. And I think that it's interesting to note in her current position, she's doing some things that philosophers of science may not always do, including working with governmental leaders in policy, including most recently the Senate and Ministry of Economics in Mexico. So with that, you can please join with me in welcoming Carina Prunkl to talk to us about how anthropomorphic is thermodynamics.
Yeah, so thank you very much, Alan. It's really a pleasure to be here. Maybe just a quick correction. As of last month, I'm actually a research fellow at the new Institute for Ethics in AI at Oxford, which is a couple of streets wide, further from the Future of Humanity Institute. But yeah, no, I mean, it's a real pleasure to be here. So the work I'm going to talk about today is very much work in progress that I'm currently doing in collaboration with my colleague Katie Robson at the University of Birmingham. So yeah, so I'm especially keen to have your thoughts and comments on the piece in the Q&A later. And of course, yours comments are also very welcome. So the question we're attempting to answer in this project is about how objective thermodynamics is. Let's see. So the idea that thermodynamics fundamentally has something to do with the human perspective is a rather old one. So Bridgman, for example, in a very fitting quote writes, "Thermodynamics smells more of its human origin than other branches of physics. The manipulator is usually present in the argument, as in the conventional formulations of the first and second laws, in terms of what a manipulator can or cannot do." And then similarly, Maxwell also talks about heat and work as being relative to an observer. So here he writes, "Confusion, like the correlative term order, is not a property of material things in themselves, but only in relation to the mind which perceives them." And then finally, Jaynes, who is at the center of the so-called information theoretic interpretations of entropy, and especially known in the statistical mechanical context, he writes, "The strong contrast between the physical nature of energy and the anthropomorphic nature of entropy was well understood by Gibbs before 1875. So this emphasis on the anthropomorphic or anthropocentric rather nature of entropy has made some philosophers rather queasy, so rather uncomfortable. And in particular, those philosophers think that our physical theories that are not depend on states of knowledge. So for example, John Doherty and Craig Callender write about the idea that thermodynamics has anything to do with states of knowledge A steam engine's efficiency doesn't care about whether anyone is looking, our uncertainty, or our beliefs. And then David Albert has expressed very similar concerns, not just about thermodynamics, but also about statistical mechanics in a now rather famous quote. Can anybody seriously think that it's somehow necessary that the particles that make up the material world must arrange themselves in accord to what we know with what we happen to have looked into? Can anybody seriously think that our merely being ignorant of the exact microconditions of thermodynamic systems plays some part in bringing it about, in making it the case that, say, milk dissolves in coffee? And so given these two very different accounts of thermodynamics and its relation to knowledge or to ignorance, Katie and I thought we better start looking and go in search of the human smell that Bridgman was referring to earlier. So here is how the chase is going to be. So I'll first start with being a bit clearer about what we actually mean when we say thermodynamics is objective, or when we say thermodynamics is anthropocentric. So it's just tidying up a bit. And then I'll start talking about the laws of thermodynamics. So especially for those who are not familiar with the topic, the idea is that just giving a brief explanation of what thermodynamics is about, but also to make a bit more explicit some of the ambiguities that exist with respect to the second law, or maybe I should rather say second laws of thermodynamics. And then finally, I'll turn towards two arguments against the objectivity of thermodynamics, and then discuss them in turn. So that's Jaynes's approach to the Gibbs paradox, and then the discussion of Maxwell's means relative view. And then finally, I'll raise the question, or I'll come back to the principal question of this talk, so how anthropocentric is thermodynamics itself. Okay, so I'll begin by saying a few words about what we might actually mean when we talk about objectivity. Here, Denby and Denby distinguish between two kinds of objectivity. So the first is objective in the sense of some intersubjective agreement and its denial, so subjectivity. And the second type of objectivity relates to mind independence, and here the denial is anthropocentrism. So there are of course other ways to make this distinction, and in particular in philosophy of physics, we often talk about ontic versus epistemic, and then there are a lot of others that fall outside the realm of a philosophy of science that I won't go much into here. But instead, I'll make use of Katie Robertson's account of objectivity. So this is basically an extension to the Nozick account, which he introduced in his invariance and objectivity paper. Here, the main idea is that objectivity is defined by invariance across different perspectives, and it comes also in different degrees. So this means basically there's not just a binary concept, but that for things can actually be more or less objective, depending on what transformations they are invariant under. So this means basically that the more observers a feature is invariant under, the more transformations a feature is invariant under, the more objective it is. Here I actually wrote observers, but possibly it's better to talk about perspectives or aspects rather than observers, in order to not bring in this human smell at this point already. Okay, so Katie has come up with something she calls the objectivity thermometer. And at the very bottom of objectivity basically is invariance with respect to observers who have different biases. Now, if we're going a bit more objective, then in this view there would be invariance across different across observers with different experimental apparatus. So here the observers are in different places. So for example, you have different labs that produce the same result. Then even more objective would be when there is invariance for observers with different credences. So basically observers who are in different epistemic situations. And it is exactly this, so it's exactly this invariance that gives rise to the possibility of intersubjective agreement that we already mentioned for Denby and Denby. And then even more objective is invariance with respect to observers that have different cognitive or perceptual apparatus. So for example, here we have two images of flowers, and one as it's seen with human eyes and one as seen from the point of view of a bee. And clearly there is a difference, and so colors could be seen as not fulfilling the criterion of objectivity in this sense. And it's exactly this type of objectivity that is at stake when we talk about anthropocentrism and thermodynamics. And finally, then there's the limit. Here it's objectivity with respect to all possible observers, so basically a God-eyes view. And what I'll be concerned with today is going to be mostly objectivity with respect to different epistemic situations, and objectivity with respect to different cognitive apparatus. Okay, so before talking more about objectivity, I'd briefly like to introduce the laws of thermodynamics. Not all of them, but some of them at least. And I'll start with the most fundamental one, which is the minus first law, as it was introduced by Harvey Brown and Jos Uffing. And it basically states that unless a system is subject to external change, it will spontaneously attain and remain in a unique state of equilibrium. So basically, no matter what the state the system was previously in, it will move towards that unique state of equilibrium. And the time asymmetry that we often associate with thermodynamic behavior is traced back to this very fundamentally asymmetric law. So the minus first law also implies that two systems that are brought into thermal contact equilibrate and then reach a unique equilibrium state. Now, the first law defines heat and work, both very fundamental concepts in thermodynamics. It states that the internal energy U of a closed system can only change by either adding heat, dQ here, to the system, or by performing work, dW on it. And we can understand work here as the transfer of mechanical energy. So for example, the raising and lowering of a weight in a gravitational potential would count as such a transfer. We can also call this usable energy transfer. And in fact, a lot of textbooks do that, because we can actually do something with the energy that we're transferring, or that we're extracting from the system. And then heat, by exclusion very much, is the transfer of non-mechanical energy. So basically, it does not lead to the raising or lowering of a weight. And it's also sometimes referred to as unusable energy. So there are the two things here that I actually want to point out at this stage. The first thing is that the talking of usable and unusable energy already brings in the observer. So I marked this here as a little man or mannequin whenever there's something like this going on. So it's already bringing the observer into the thermodynamic picture. Because we can now, of course, ask usable by whom and usable how. The second point is that, strictly speaking, work and heat are not forms of energy. So a system does not contain a certain amount of heat or a certain amount of work, and hence there are the inexact differentials here. So rather, what's happening is that we have a given process the system is undergoing, and the process is characterized by the amount of heat the system exchanges and or the amount of work the system that is performed on the system. So the first law basically restricts these types of processes that a system can undergo. Okay, now to the second law, and certainly the most controversial of the laws of thermodynamics. I think it's useful to first start with its origin, which was arguably by Carnot. So Carnot established that for two heat reservoirs at temperature, say hot and cold, all heat engines that operate between the two reservoirs are less efficient than a reversible heat engine. And then moreover, all reversible heat engines operating between two reservoirs have the very same efficiency. And then notably, and actually also quite importantly, the maximum efficiency of a heat engine is completely independent of the working medium that is used. So basically, it allows for the description of a thermodynamic system as a black box. Yes. Okay, so then Clausius makes the observation that heat everywhere exhibits the tendency to annul differences of temperature and therefore to pass from a warmer body to a cooler one. Now, just to point out that this is an empirical observation of the behavior of bodies. And from these two, then, it's possible to derive what I take here to be the second law of thermodynamics, which basically reads, it is impossible to perform a cyclic process which has no other result than that heat is absorbed from a reservoir with a low temperature and emitted into a reservoir with a higher temperature. So this is the Clausius version of the second law as cited in a paper by Joseph. And I want to draw special attention here to the fact that the process is cyclic. So that means the system actually by the end returns to its original state, the end of the cycle. Okay, so far so good. But then things got a bit more complicated with the rise of kinetic theory of gases and the identification of the temperature with the average kinetic energy. So basically, Maxwell showed that the velocities of the molecules in a gas are not uniform. And so when there are random movements and constant collisions, the average kinetic energy of the subset of the gas may actually differ from the average kinetic energy of its neighbor. So as a result, we have temperature gradients within the gas. And so it seems actually as if the second law, or rather what has served as the very foundation of the second law, namely that heat flows from cold to hot, is constantly violated on very small scales. So there are different ways one may respond to this and this was also how Maxwell came about his famous Maxwellian demon, and that he thought, well, a very neat-fingered being could possibly exploit these little temperature gradients and violate the second law. Now, there are different ways how we might respond to this violations or this apparent violation, and they result in very different takes on how we understand the second law. So the first one is to just concede that the original second law is violated on small scales, and then to consider the second law to be statistical rather than to be a statistical rather than a mathematical truth. And in this sense, the second law would in particular only hold for macroscopic systems. For microscopic systems or for the subsystems of the big systems, it would become quite useless. So the second law holds as long as there is no way to distinguish between the individual molecules, as would not be possible by a macroscopic observer, basically. Now, the second way out of this dilemma is to change the content of the second law. So here, the idea is that the second law is changed so that it contains the fact that violations have to be performed reliably in order for the second law to be actually violated. So here, the probabilistic second law would read: second law prohibits the reliable conversion of heat into work from a single reservoir, made precise by the notion of expectation values, for example. And now, just to point out that here we would need to make use of probabilities in order to make these expectation values precise, which in themselves raise important questions about ignorance and the role of the observer. So I'll only very briefly address probabilities and statistical mechanics here, because I'm mostly concerned with macroscopic thermodynamics. Okay, so I think these, it's actually quite important to keep these different second laws in mind. And in fact, I think if everyone always kept them in mind, then we probably have a lot less misunderstandings about the foundations of thermodynamics and statistical mechanics. Right. Okay, so we can now start discussing whether thermodynamic raises questions for objectivity. And I'd actually like to start with a discussion of the denial of objectivity as intersubjective agreement. And to do so, it's useful to consider a paradox that was originally proposed by Gibbs, the so-called Gibbs Paradox. And it goes as like the following. So consider you have a box that contains two monoatomic gases, which are separated by a partition in the middle. So that would be here. But so both of these gases have the same temperature and the same pressure. So the partition is then removed, and after the gas has settled, the mixture has settled again into equilibrium, we just reinsert it into the box. Now, Gibbs's paradox is that depending on whether the molecules belonging to the two gases differ or are the same, the entropy behaves differently during this process. So you can see here on the left-hand side, the entropy increases, which we also call the entropy of mixing. And on the right-hand side, the entropy remains the same. And this increase, importantly, is also predicted even if the gases share all the relevant properties. So they may have the same mass, they may have the same charge, they may have, they may even be moving on the same trajectories. If there are two unknown elements that human beings have never come across that we think are the same, because they behave the same in all relevant aspects, there would still be an entropy of mixing. Now, Jaynes said, now consider two observers. Consider two observers, Alice and Bob, and these two have different information about the gas. So Bob thinks the box contains two gases that are two gases that are the same. But Alice knows that there is a difference between the two gases. So she knows that the one gas is actually different from the other one. And then suppose that Alice inserts a semi-permeable membrane into the box and then extracts some works. So the idea is then that it would look for Bob as if Alice had just violated the second law by extracting work from a single reservoir without any compensation. And now Jaynes's take on the Gibbs paradox is that it basically shows that entropy is relative to the knowledge of observers. So, and this is again this way of understanding entropy as relative to the knowledge of Bob and Alice. We see here that Bob's characterization used those macro variables x1 to xn. Alice had access to another macro, to another variable, to more information, and so she was able to extract some from the gas. And this idea that entropy is relative to the knowledge of observers is very popular in the physics community as well. So here, Philipp Feist and Renato Renner, both at ETH in Zurich, write, our framework naturally treats thermodynamics as a subjective theory, where a system can be described from the viewpoint of different observers. So this means basically that according to their view, there does not need to be any intersubjective agreement in thermodynamics. So this is basically a denial of objectivity in the sense of objectivity being an intersubjective agreement. Okay. But there are some problems with this view. And in particular, yes, sure, there is intersubjective disagreement between Alice and Bob, but if Bob thinks that Alice has violated the second law, then he's just wrong. So at the end of the transformation, the system is not in the same state it was previously in. So the system de facto has not returned to its original state. And also, Alice cannot repeat her little trick. So basically, the argument that thermodynamics itself might be subjective in this way does not really go through. And then Jaynes, of course, when he made his argument, he had in mind his statistical mechanical framework in which he takes probabilities to be representing states of ignorance. So there's a strong motivation for him to also take thermodynamic entropy to be associated with ignorance. But really, there is no reason for why one should do that at this point. Okay, so but maybe entropy does not depend on our epistemic states, but instead on the practical possibilities of performing operations or on the available means that determine such possibilities. And this was exactly Maxwell's take. So here Maxwell writes about the second law. The second law is equivalent to a denial of our power to perform the operation just described, to transform heat into ordinary motion, either by a train of mechanisms or by any method yet discovered. Hence, if the heat consists in the motion of parts, the separate parts which move must be so small that we cannot in any way hold of them to stop them. So this leads us to another denial of objectivity, which is the denial that two observers with different cognitive or different perceptual apparatus agree. So basically, it brings us to anthropocentrism. Finally, so there are at least two angles, two anthropocentric angles to Maxwell's view on thermodynamics. The first is that the distinction between heat and work is anthropocentric. The second is that the violation of the second law depends on the available means, in turn are anthropocentric. So let me just begin with the distinction between heat and work. So again, I want to point out that this is something one finds often in the literature. So here is Eleanor Knox from King's College, for example, who writes, the distinction between work and heat must be something like the distinction between the kinetic energy associated with random chaotic motion of molecules and the kinetic energy associated with aggregate motions of molecules. But even if we can find some way of carving these up, it's hard to see how this could be a natural distinction. After all, from the perspective of kinetic theory, it's all just kinetic energy. And then Maxwell himself also writes, confusion like the correlative term order, and we've already had this earlier, is not a property of material things in themselves, but only in relation to the mind which perceives them. And similarly, Mervold writes about Maxwell, the distinction between heat and work seems to rest on anthropocentric considerations, or better, on considerations of the means we have available to us for keeping track of and manipulating the molecules. Now, one thing to notice is that by now we're actually moving from thermodynamics to statistical mechanics. So thermodynamics by its nature is not concerned with the movement of individual molecules. So it rather, as we showed earlier, it looks at systems as black boxes. And because we're moving into statistical mechanics, we can also respond to this worry about anthropocentrism with statistical mechanics. And basically, both in classical and in quantum mechanics, in quantum statistical mechanics rather, heat and work are very well defined, and they do not need to be understood as being anthropocentric. Now, as long as we don't interpret the probabilities as subjective, then heat and work are also not anthropocentric either. So here, the change in the average for quantum systems, maybe I shouldn't go in this. Also, I just realized there is the heat actually does not only depend on the Hamiltonian of the system itself, but also on the interaction to another system. So here there's a small error. But basically, all that I want to show here is that as long as we don't understand these expectation values that we are very familiar with in quantum theory as subjective, then there's no reason to think why heat and work, or the distinction between heat and work, should be subjective in quantum thermodynamics. Okay, so let us now think about the violation of the second law. And let's go for a moment back to the Gibbs paradox. So Maxwell writes that to say that two gases are thermodynamically the same is just to say that one cannot distinguish the one from the other by any known reaction. So this raises then in question whether, as a result, changes in our technical abilities will actually lead to different thermodynamic descriptions of the same systems. And as Mervold stresses in his paper on Maxwell, it's for Maxwell, no matter which physical principle precludes the operation of a Maxwell demon, it is only our current but perhaps temporary inability to manipulate molecules individually that prevents us from doing what the demon would be able to do. And then this again brings out Maxwell's view on the second law. For Maxwell, the second law is a practical impossibility rather than a nomological impossibility. But we know that if we work with the probabilistic version of the second law, for example, that requires us to have a reliable conversion of heat into work, then demons, as the one Maxwell proposes, are physically impossible. So, and by now there is quite a lot of versions of what is known as Landauer's principle that actually show this physical impossibility of having a Maxwell's demon. So Maxwell's argument for anthropocentrism doesn't seem to have any teeth in this case either. Okay, so maybe let me summarize Maxwell's view. So for Maxwell, thermodynamic is anthropocentric because the heat-work distinction depends on the mind that perceives it, and because he takes the reason for us not to be able to violate the second law to be the fact that we are having just big clumsy fingers, so we're not able to manipulate the molecules. And this brings us to what I think may be the more controversial part of the evening. The question is whether Maxwellian means relative approach, namely that the thermodynamic entities are relative to the means an agent has, would actually commit us to anthropocentrism, even if we look at the probabilistic and thus nomologically strict second law. So let me just give a very rough overview over the chain of reasoning that has been deployed by Maxwell up to Jaynes. So Maxwell argued that heat work and entropy are means relative concepts, and the question then arises whether means are determined by what an agent knows or can know, and from that is then just a very small step to claiming that knowledge is fundamental to thermodynamics, as in fact then Jaynes did. Now the question I'm interested in is whether a means relative approach actually commits us to anything of the sort. So does it actually commit us to having the means being determined by what an agent knows or can know? And I actually think not. And for this, it's quite useful to set up the means relative framework in slightly different terms. So we have the laws of thermodynamics that restrict the set of processes a system can undergo. And we specify a process by an operation O and a set of thermodynamic state variables here, labeled x, y, x1 to xn. And then the thermodynamic state space, and this is very uncontroversial, is the equilibrium state space. And so already by construction, external operations are required. So there really is an implicit agent present in thermodynamics who obviously does not need to be a human agent. It could be a memory cell or a machine or something. Anything that pushes the system. So then a means relative approach to thermodynamics would be something of the following. Thermodynamics is about which processes a system can or cannot undergo given a set of operations O and an agent who can perform, given the set of operations O, an agent can perform on the thermodynamic system specified by a set of variables x1 to xn. Now there's two things to remark here. The first is that entropy remains relative to a set of macro variables. But then, this, of course, quite trivially, does not really imply anthropocentrism. So in fact, there are a lot in physics. We have a lot of entities that are relative, and equilibrium is one of them. It's relative to a set of variables. Kinetic energy in special relativity is relative to a given frame of reference. But there is an objective fact about what the kinetic energy of an object is with respect to this given reference frame. So at least the relativity of entropy should not worry us too much, and certainly is not sufficient for anthropocentrism. Now, the second and I think more serious worry is that the choice of variables that determine the thermodynamic state in a means relative approach are determined by the means. So then the natural question to us is, how are the means themselves determined? And again, I don't think knowledge is the only way to think about them. So it seems to me that at the heart of a means relative understanding is that there are different levels of descriptions of the system possible. So the choice of variables in principle is a free one, and we could use a very fine-grained description, but in practice it's constrained, and there are very clear rules about which description seems more appropriate for which purpose. Just going to peek at the clock. Okay. There are further merits of a means relative approach when expressed in the terms of a set of operations and a set of specified variables x1 to xn. And one of them is that it carries over to quantum mechanics, and it actually allows us to derive the entire equations of thermodynamics from quantum mechanics. So it allows us to really derive a thermodynamic, the laws of thermodynamics from quantum statistical mechanics, and so also from the laws of quantum mechanics. But unfortunately, I won't have time to go into this. But it very much relates to the resource theoretic approaches to quantum thermodynamics. Okay, so one last point I'd like to make before I'm letting Jos speak is that thermodynamics, of course, is not fundamental. So the macro descriptions, such as those that we see in thermodynamics, are not fundamental. Thermodynamics is a macro, is not a fundamental theory, and so for some conceptions of objectivity, the fundamental is privileged as the most objective because it carves nature at its joints. But so thermodynamics is not objective in this way. But I don't think this allows us to call entropy subjective, because we actually have a lot of theories that are not about carving nature at its joint, and that we would still not call subjective. So when we connect objectivity to epistemic virtues, then thermodynamics certainly is very epistemically secure. Okay, so I will very briefly conclude. So I talked earlier about various notions of objectivity, in particular, talking about Robertson's approach for having objectivity that comes in degrees. I made the point that thermodynamics is not related to knowledge, at least not in a worrying sense, as Jaynes wants us to believe. I showed that thermodynamics can be understood in terms of means, and that entropy is relative to a set of variables, which is not problematic, but possibly having this choice of variables could be problematic. And then finally, I just briefly mentioned that thermodynamics is not fundamental. I think it's also important to say what I didn't talk about, which are probabilities in statistical mechanics and in quantum statistical mechanics. And especially in classical statistical mechanics, probability, one of the difficulties is to, especially in the Gibbsian approach to statistical mechanics, is to think of probabilities in any objective sense. Now, in quantum statistical mechanics, I think life gets much easier, which is good, because quantum statistical mechanics is our most fundamental statistical mechanics. So here it very much depends on how we interpret the probabilities that arise in the quantum context. where I think, and there I think it's more straightforward, or there are more reasons to think these probabilities are objective rather than epistemic, ontic, or rather than epistemic in nature. Okay, so thank you very much. I'm giving over the floor to Joost now.
Thank you, Carina. And let me just say, while Joost is getting set up, that part of our format for the International Postdoc Forum is to have a short commentary from someone at the University of Minnesota. And today I'm delighted to introduce my colleague, Joost Uffink in the Department of Philosophy to offer those comments. Joost.
Well, thank you, Alan. And more importantly, thank you, Carina, for this lovely talk. I will have a few comments on it as I was asked to prepare. And let me share my screen with you. But let me start basically by saying that I agree with almost everything I heard. And so most of my comments are either, if they express disagreement, it's about people that you have quoted rather than anything what you have said. And further, I would like to present perhaps some alternative ways to make the same points I think that you are making. But basically, I certainly agree that regardless of whether thermodynamics is fundamental or regardless of whether it's means relative in any sense, all those senses do not lead to the conclusion that thereby it becomes subjective. So the first issue I want to raise is about this human smell that Bridgman brought up, when he said that thermodynamics smells more of a human origin than other branches of physics because of the presence of manipulators in its formulations. I'm not sure I agree completely with Bridgman here. And here's a point that you also already brought up, that one could say that this human smell, with an emphasis on humans and observers, and is also present in other physical theories, like special relativity. And they also have, and they're also dependent on certain processes that the observers can or cannot do, cannot perform, like sending signals faster than light. I think this presence of, or the constant reference to human observers and their observations is not too surprising, because it's actually, these both are theories that heavy spell of empiricism as a view on the goal of what science should be. And one can, of course, debate the question whether this reference to observations and thereby implicitly to humans is desirable or not. But it's not unique to other theories of physics. But I do understand the sentiment that Bridgman expressed, although other authors, and I'm thinking here particularly of Tatjana Ehrenfest, have expressed it rather differently, or expressed it more pointedly by pointing their fingers to just a subgroup of human beings, and that's the engineers. What Tatjana Ehrenfest van der Schever points out is that thermodynamics was handed to us, to the physicists, by the engineers. The engineers who, since the late 17th century, were involved in building heat engines and trying to improve their efficiency. And so all of these important people involved in that, Watts, Carnot, Clapeyron, Joule, Rankine, and others, they were all engineers. Maybe Carnot was an exception because he was really a officer in the French army, but they still took this engineering approach to develop the theory of thermodynamics. And this is a very different attitude to what later theoretical physicists would take in trying to develop as physical theory. Engineers, it's rather natural to consider they have goals and they have means to try and achieve those goals. For example, their goal might be just to build the most efficient steam engine possible. But they're less interested in finding something like an objective view of nature that would advance our understanding of the physical world. And here is one way in which you could try to illustrate this difference. You mentioned the Clausius formulation of the second law, and there's also the Kelvin formulation of the second law, which is slightly different, but it says simply that it's not possible to construct a cyclic process which has no other result than that heat is absorbed from a single reservoir and useful work is performed. Now, I want to draw an analogy here between heat engines and, say, an electrical engine. And if you want to make that analogy, you also have to replace the notion of heat by electricity and then temperature by the electric potential. If you make those changes, you get a statement that says it's not possible to construct any electrical engine that will perform a cycle and which has no other result than that electricity is absorbed from a single potential while performing useful work. Now, in all respects, that statement is actually true in electrodynamics. And one could see if I can move. Yeah. If ever you find with only one prong that would allow it to connect to just a single potential, then it's not going to work. So, in spite of the fact that this statement would also be true in electrical theory, nobody who had ever seriously considered making this the foundation of electrodynamics that would make this in the fundamental law of the theory. So why is that? Electrodynamics on laws like these. And that, I think, is basically that people working in electrical theory were much more of a theoretical physics declination than they were of an engineering declination. Of course, it's also historically the case that at the time when Maxwell started to develop electrodynamics, there were very little to none electrical appliances around to base his experience on. And so electrodynamics was much more theoretical from the very start. So this was meant to illustrate or make the point that there is this strong engineering attitude in the history of thermodynamics that for many later physicists was something that needs to be overcome and to be replaced by a more theoretical approach. And again, one might debate whether this is a good thing or a bad thing, and I don't want to take any issue in that debate here. So except to say that there have been attempts to try and formulate thermodynamics in a way that is more to the taste of present theoretical physicists and increase the rigor of the approach and define the fundamental concepts. So let me turn to the distinction or the concept you brought up, the means, the minds, and the agents. I fully agree that thermodynamics does assume that there is a distinction between heat and work, and it also assumes a distinction between whether thermodynamical states of a system are the same or whether they're different. And your paper showed that in the discussions of the Maxwell demon and the Gibbs paradox, those distinctions become less secure when we move from thermodynamics to the kinetic theory of gases or statistical mechanics or indeed quantum mechanics. And it's noteworthy that this only happens when we already adopt the background of another theory than thermodynamics itself, which, as you rightly pointed out, is quite neutral with respect to what the constituents of the thermodynamical systems actually are. So this is apparent both in Maxwell's discussions of the Maxwell demon, that he is adopting this background viewpoint of the kinetic theory of gases. And it's also true for Gibbs's argument about the Gibbs paradox, in which he discusses the molecular motions of the molecules in the gas. Now, let me say a few more words about Gibbs paradox, because the argument he presents was actually somewhat prophetic, which was given in 1860, when I think the concept of isotopes were not discovered yet. But after the discovery of isotopes, it is clear that there are gases and chemical elements that will typically be mixtures of different isotopes, would have exactly the same chemical properties. And so if all the means that are available to us are the chemical processes, we could not distinguish or separate these isotopes, even though they can be separated in machines like ultracentrifuges or synchrotrons. And when you ask whether these means are available to us, it's good to remember that during the development of the atomic bomb in the Second World War, it was actually the separation of the isotopes of uranium that involved the largest amount of work in the entire project. There were hundreds of thousands of people working in factories just trying to isolate the isotopes. And the means that had to be available is, well, best illustrated to me at least when I read in Richard Rhodes' history of the atomic bomb project, that the entire reserve of silver stored in the Federal Reserve here in the USA had to be melted down into wire to build enough magnets to build all the synchrotrons involved in the production of the atomic bomb. So that's the amount of means that have to be available to you to actually do this. And here I will come back to what you said, is even if the question whether thermodynamical states are the same or whether they're different might be relative to the means we have, that doesn't at all imply that the second law becomes subjective. And let me finish by trying to make that same point in a different way. So suppose we have one community of agents which only has the mean to distinguish gases or chemical elements by chemical means, and that there is another community that also knows how to separate isotopes. Now, in the first community, if you are running a steam engine, it will produce a certain amount of entropy when you regard just steam as a single gas. But in the second community, there are other ways to distinguish light water from heavy water, in which the hydrogen has been replaced by deuterium. And then the entropy produced if you're actually mixing light water with heavy water, unknown to the members of the first community, the production of entropy will actually be higher. So there is a difference between those communities whether entropy, or how much entropy will go up. And yet, that doesn't make it subjective, because in thermodynamics, first of all, it's only the temperature differences that are measurable, and the absolute value of entropy plays no particular role. It's just a convention you can set into any value you like. But more importantly, I think, there is still an asymmetry between those two communities. It might be that there are unknown means of separations to the first community that the other ones know, or that might later become known to the first community. But if they do have means of separating systems, which they know of, they cannot later become unknown. Or to put the same point differently, whether you regard two thermodynamic states to be the same might be something that is relative to your means, and that you might have to change your verdict after you discover that what you regarded to be the same actually turned out to be different states if you have more means. But the situation is asymmetrical. It cannot be the case that if you take two thermodynamic states that the first community regards to be different because they have the means to distinguish them, will later on become regarded as being the same when you discover more means of separation. If there is a distinction between those thermodynamic states, that distinction will not later become obliterated. And that, I think, is this asymmetry shows that it's not just a purely subjective matter, where it's just a question of, oh, you know, it's dependent on the perspective of the observer, and both observers have, or both communities have an equal right to claim that what they are saying is correct. There is an asymmetry here in knowledge, and that, I think, is already important enough to show that it's not subjective. And this is all I had to say. Once again, I congratulate you, and because I think it was a very well presented and beautifully argued talk. So I'll give the word back to Alan.
Thank you, Jos. So at this point, we'll bring Carina back to the front, and I will give her first opportunity to say anything she would like in response to Jos. But before I do that, let me highlight that for those who would like to ask a question, we've got two options. One is that you could put the question in the chat box and I can read it out. Alternatively, if you want to ask your question yourself, just punch the raise the hand button, and that will indicate to me that you have a question, and then I can unmute you so that you can ask that question directly to Carina. So Carina, I will start by giving you just an opportunity to respond to Jos's commentary.
Yeah, thanks. So yeah, thank you very much, Jos. Your comments were incredibly insightful, and I think especially your last point about the asymmetry is certainly something that we haven't talked, and that seems like a very powerful addition to the argument. So yeah, thank you very much.
Okay, so first question from Terry Bristol. Terry, you should be able to talk now.
There, now?
Yes, we can hear you.
Okay, so very nice presentation, and it's nice to see someone as brilliant as you getting into this dialogue. So I put a couple of comments in the chat, just things I think you would benefit from reading. My colleague Hasuk Chang has a great book, which it happens I just reread, called Inventing Temperature, and he challenges. He goes into what it is to measure something in particular, and challenges the idea that there is objectivity in thermodynamics, and he goes well into his philosophy of science stuff. The other one, so I think that pertains to the objectivity question that you're raising. I think you would find that quite interesting. Second is my colleague Peter Atkins, who's there at Oxford, I think still, and I've been going back and forth with Peter and stuff. But he had a book, one of his books is called The Second Law way back, and in it, about page 6 or something like that, he says, well, of course, there were two histories of thermodynamics, one coming from Clausius Boltzmann, and the other one from the Carnots. And he said, and both these are still alive and well. And I go like, wait a minute, that's what I was taught. I was taught that Boltzmann and Clausius won, and that's the dominant thing. And this Carnot and caloric, these are sort of historic footnotes. It took me 3 years to convince myself that Atkins was right. There are actually two versions going on. We might call the physicist version of thermodynamics and the engineer's version of thermodynamics. So I was very pleased with Uffing's highlighting of the engineering perspective. And what I'd say is that you're kind of stuck in, I would suggest, you're kind of stuck in the physics version. You're buying into a lot of the things that they're putting up. I mean, the first law itself, what they call the first law, is conservation. And, conservation is not an empirical result, it's an assumption. And likewise with symmetry and so forth. And say Sean Carroll, if you haven't read, I didn't mention Sean Carroll, he's at Caltech, has a book called, I think it's called From Eternity to Here, which I think is one of the best treatments of really going in depth into the Boltzmann-Clausius thing and about the about entropy and so forth. And one of his comments in there is to say, like, well, look, if this is right, then if you just came across the universe, sort of like ours, you would what state would you expect it to be in? And he goes like, overwhelmingly in equilibrium. And so he says, well, so how do we account for our universe? Now, if entropy is always increasing, even statistically, then the question is, how did we get to a low entropy state to begin with? I have a talk that I gave that's like, well, it's like all the water is running downhill. And if everything is running downhill, then how'd the water get up there to begin with? It's essentially the same problem. And this is just not addressed. I mean, Sean Carroll says it. He says, well, there's just, if all entropy is going forward, there's no possible account within standard assumptions that defining modern physics that we could have a low entropy beginning. It's not that we don't know the answer, it's just there's no possible answer, okay? Final thing I would highly recommend, because this happens to be what I'm working on, that you would read, I'm sure you know a lot of Sadi Carnot, but you should read Lazare Carnot. Lazare was Sadi's father. And he, in my opinion, was a real genius. Sadi is simply a mere application, as they say, of what Lazar came up with. And Lazar really gets into, as an engineer, he starts out being not happy with rational, he calls rational mechanics, which is, again, the physicist version. And he goes, in particular, because it doesn't account for engineers in engineering. He talks specifically about the trade-off of velocity and time and power, which is, anyway, you'd have to read it. But, and in it, particularly if you look at I put it up in the deal, the foundation, fundamental principles of equilibrium motion, in the last section of that, he goes right into seeing us as thermodynamic engines ourselves, essentially. We're engines, and he translates all of thermodynamics into human work and talks about horsepower and all that sort of stuff. Really cool stuff. And there's a lot of that. I also recommend Don Cardwell, who I think understood that we have, unfortunately, as historians of science, have gone back and tried to reconstruct the history of science on the assumption that modern physics is a mechanical theory, and the end point of modern science is going to be a mechanical theory. Therefore, the history of science must have been mechanical. This is Kuhn's objection and so forth. But Cardwell has some, he says, I think this might be to take too narrow perspective on the history of thermodynamics. Anyway, well, enough. Thank you for your talk. I might send you some stuff.
Alan, I assume I'm just commenting or responding.
Yeah, go ahead, Carina.
Okay, good. Yeah, so thank you very much for these recommendations. I definitely take a look. I have heard of Peter Atkins's Second Law. I think I browsed it once. I didn't go into enough detail to look at the two histories of thermodynamics. Looks very interesting, and it seems I'm almost dreading opening it and discovering another version of the Second Law, because I think already in physics, when we're looking at the way the Second Law is discussed, especially in the quantum context, we already see that there are all these different ideas of what the Second Law means and how it's being used, and also how work and heat are interpreted. So there's now all these quantum work engines, etc. But yeah, so I definitely have a look. Regarding Sean Carroll's book, I'm also looking forward to reading that. I know that David Albert famously has worked on the past hypothesis, and Boltzmann himself also wrote about this problem, and David Wallace has also done some work on this. So I don't know whether if that might be of interest to you. And there's also some work in quantum mechanics that looks at the beginnings of the early states of the universe, and looks at the initial conditions in order to explain these things. But yeah, no, I'm looking forward to reading all the literature you recommend. Thank you very much.
So I've now got a question in the chat. So let me go ahead and give that. So it says, for Jaynes, the main thing was relative entropy, since it is valid both in discrete and continuous cases. And when you adopt relative entropy perspective, you have priors and posteriors, and hence updating beliefs, subjectivity, etc. What is your opinion on this?
Yeah, good question. I don't know what my opinion on this is, to be honest. I think, Jaynes famously tried to make the whole epistemic machinery, especially in the statistical mechanical context, where he was working a lot with the Gibbs entropy, tried to make it objective. So he was actually talking about objective epistemic probabilities, rather than normally we think epistemic probabilities are not objective, or they're on take, or at least that's the way the word is used. I personally find it hard to think of updating in classical statistical mechanics. I guess I find it hard to find justifications for the coarse graining, and thus for the increasing entropy in a system, without appealing to something like ignorance or states of knowledge. But possibly, in the talk I said, I was arguing that we should be able to think of things relative to relative to a certain variable. So possibly the same would go through in statistical mechanics. But I actually haven't thought about I haven't thought a lot about the classical statistical mechanical case. I know that in the quantum statistical mechanical case, things are becoming much simpler, and we actually don't need to refer to these epistemic probabilities. But yeah, no, it's a good question, and I certainly should think more about this.
So we have one more question in the chat. So you cited resource theory of thermodynamics, but as we have recently seen in a paper by Lostaglio, resource theory is far from yielding the results obtained in experiments in which calculations are done through Lindblad equations, that is, open systems approach. They are not equivalent. Hence, I would be careful in citing resource theory as a successful attempt, at least not yet.
Yeah, I mean, I'd be curious if the speaker would like to step up and speak about the details. What exactly has been shown? Was it just shown that the theory that it's hard to make experiments because we're not able to manipulate quantum states sufficiently, or what the problem was?
So I will let them raise their hand, or if they want to correspond with you later, that's fine too. If that's
maybe that's easier. Yeah.
Let me turn then to the next question that I have in the queue, which is from Mauricio Suarez. Mauricio, I'm going to click on your microphone as soon as I find you in my list, and there you go.
Can you hear me now?
Yes.
Oh, okay, so great talk, Carina. Really nice to see you. And I was just wondering if you've looked into the manipulability theory of causation. And the reason why I suggest that you may want to look into it is that there is this notion of invariance of a causal relation under interventions on the putative cause that may well suit you in and support your thesis of how there can be means that are not relative to knowledge or relativistic in that spurious sense, but objective. They have a very similar take on interventions as objective means. And I even had a PhD student some years ago write a thesis on causal interventionism in statistical mechanics that you may find interesting. So I could ask her to send you her PhD thesis. You may find something of interest there. Thank you very much for the great talk.
Yeah, thanks a lot. Yeah, that's very useful. And I guess this is like also one of the great benefits of being in a forum or being part of a seminar where there's so many people with interesting backgrounds in philosophy of science and history of philosophy. So yeah, thank you very much. I guess we can get in touch via email to for you to send me the paper or the thesis or your PhD student.
Okay, so I've got a couple more hands up now. So next question from Barry Mingst. Barry?
Hear me?
Yes.
Thank you, Carina. Quite interesting talk. This comment is coming from an engineer. My apologies. I have first a comment. I think you may be misrepresenting Maxwell's view. I've worked a lot with Maxwell's derivations. I don't believe his view was actually practical. Now, practical interpretation is not unreasonable, but I don't believe that Maxwell actually would have bought into that. If he had, I doubt he would have come up with his demon in the first place. However, my main comment is more along the lines of, again, looking at Maxwell's derivations. If you keep in mind the starting assumptions for all of those thermodynamic laws, they're driven by the movement of particles that are defined to have no internal forces and no external forces. That is, no van der Waals and no gravity. So I don't see any dichotomy or paradox in the fact that the universe is clumpy instead of uniform, because we do have gravity, and that kind of short circuits the whole laws of thermodynamics to begin with.
Yeah, thank you very much for this. So maybe just on Maxwell, you're saying he's not practical, otherwise he wouldn't have even come up with his statement. I agree that he's not practical. I guess the distinction I was trying to make was between in practice and in principle. So by in principle, I mean ruled out by our laws of physics, and by in practice, I mean not ruled out by our laws of physics. So this was very much the distinction that I was trying to make when I said he adopts this view that the second law is can be violated in principle. So, and regarding the starting assumption of the yes, no, I completely agree that the thermodynamically favored state is the once we start using gravitation is the one where matter lumps together. But I think you'll still need to have a low entropy state at the beginning in order to explain the current evolution of moving towards a higher entropy state of the universe, if that makes sense. But I do recommend David Albert on this and David Wallace on his past hypothesis. And I think especially David Wallace explicitly addresses also the fact that obviously like lumpy matter due to gravity is matter in low entropy state. But thank you for the comment.
Okay, next I'll go to Sam Fletcher. Sam?
Hi, Carina. Thanks so much for helping me get clarity on this issue that I've been thinking about this week in preparation for your talk. It's one of these topics where when you first learn about it, you get this sense of vertigo. Now I'm just getting the sense of stabilizing myself. I think that one of the things that I learned from your talk was that one way of understanding the means relativity is that it is about the thermodynamical accessible processes, what states are accessible from others, and that different sorts of means enable different sorts of paths in the thermodynamical state space or describe new classes of variables in that state space. And indeed, this doesn't entail anything about subjectivity or being perspectival. But I was hoping that you could then return to the question of what implications this has for our understanding about the difference between heat and work, and maybe also the second law. Would the idea be that for a given physical process, the distinction between kind of like the heat transfer involved in the process and the work done in the process are going to be relative to that kind of background description of what processes are, what states are accessible from what others, and what variables there are. If that's right, then I guess the idea is supposed to be something like heat and work themselves are things that instead of measuring directly, we only measure through the conceptual apparatus, the theoretical apparatus of a particular thermodynamical state space with particular accessibility relations on it. Does that seem like that's the thing that I should be taking away from about heat and work, or would you suggest a different way of thinking about them as a result of this this point of view?
And at first, as a first go, I would say yes, that seems right. But I probably wouldn't want to. I probably would like to think a bit more about how you phrased it to make sure I understood it correctly. So maybe again here we could talk separately about this, because I think it's a very good point. The way I addressed the heat work question here was actually mainly on the statistical mechanical front by saying, the main worry of the heat work distinction breaking down is when we move into kinetic theory and when we move into statistical mechanics, and not not within thermodynamics.
Right. Good. Right. So, but one of the things that I took from Jos's comments, though, is that if one sees this issue as an issue about thermodynamics proper, rather than an issue about statistical mechanics, which through its different conceptual apparatus affords different responses and different answers, then we can set aside the question of what that distinction is supposed to be in statistical mechanics and ask whether or not thermodynamics has any resources to answer this question on its own. I think it would be very interesting if the answer is no. Then in fact, we have to rely on statistical mechanics on determining how to make this distinction. But it would also be very interesting if the answer were yes. If the answer were yes, figuring out what the details of how the yes answer went would also be very interesting.
Yeah. Let me think about it a bit more.
Mm-hmm. Sure.
Okay, we have time for one last question. And so I'll go to Alok. You can unmute yourself and ask your question now.
Thank you, Alan. Carina, thank you. That's extremely well-constructed talk, a lot of it new to me. And I want to try and see, I guess, some part of your next talk. I really appreciated the construction using Katie Roberts' objectivity thermometer and the gradations of test and concur between two parties. And if I bring in what Jaynes brought up, the two communities way of talking about it, that the Atom Bomb Project produced a community that added manipulation capacities, right? I mean, he uses the term communities. So, and you use, for the two subjective stances, you use epistemic states. And I just want to say, from a historical contingent point of view, if you replace the word states with situations, epistemic situation. So even Maxwell, when he's talking about our current capacities for manipulation, he's talking about a historical process where the situation might change. We will change it. And that concurrently, two different communities may be in different states of epistemic access or manipulation practices. What that allows for is not just a comparative process, but a collaborative metabolism of the difference between the two epistemic situations. And then you're in the world of what Tatiana Ehrenfest was saying, that the engineers had manipulation capacities, they had graphs, and then the physicists produced equations. And then you can go through something what Terry Bristol was talking about through Hasek Chang, that epistemic communities with their repertoires can be concurrently in different places, and the differences can be metabolized. So I'm looking forward to how you grow this framework, because I think it's very promising. Thank you.
Yeah, thank you very much.
Okay, well, we are at the end of our time, and I want to start by thanking Carina for her presentation and also Jaynes for his commentary. I'd also like to thank everyone who attended and for those who asked questions. We are excited that this is the first of a series, and for those who are interested, the next talk will be on December 11th by Saana Jokela, Evidence-Based Paradigm and the Challenge of Assessing Effectiveness of Preventive Surgery, with a commentator, Stephen Stovitz, here from the Department of Family Medicine and Community Health. Hopefully you will be able to join us for that, but look for further details on our website, cla.mcps.umn.edu. Until then, I wish everyone all the best. Stay safe, stay healthy, and take care.
Thank you.
Thanks a lot.